Okay, so how's everybody doing? Everybody okay? Any questions?
I posed a question on the SQL.
Yeah.
There was an arbitrary proof that I didn't really comprehend why they did that.
Which one?
The n, so start from n is greater than y and move on to there exists a rational n over n, which is
Yeah. Okay, we're gonna do that. Don't worry, we're gonna do that. Yeah. Okay. So first off, we're gonna do something which is maybe not so interesting. Let's reveal. We're gonna do properties of fields. So I'm not sure how much I'll do of this, but let's get to it. So recall first. So we're going to be doing properties of fields. Okay, and so recall the field axioms. Right. So a field is something that has a plus and a dot. Right. So you've got this set of elements. It's got some something that acts like addition, something that acts like multiplication. And then the addition, has to satisfy closure, right? It has to satisfy commutativity. It has to satisfy associativity. It has to satisfy the existence of an additive identity, right? And then there are corresponding properties for multiplication, right? That it has to be closed under multiplication, right? You don't want to multiply two things and get something that's not in your field, right? It has to satisfy multiplication must be commutative, multiplication must be associative, and there must be a multiplicative identity, right? Which is normally called 1, just like this guy is normally called 0, right? And I think Rudin says that he doesn't want to have fields that have only one element. You can, somebody asked about this in the SQAs, you can have a field with only one element, 0, right? And so, that field of one element, it's closed under addition because 0 plus 0 is 0. It's commutative because 0 plus 0 is 0 plus 0, and so on and so forth, right? Right, and you could use that 0 as the multiplicative identity as well, and everything would be satisfied. But that's sort of like a not that interesting field, and so we just exclude that as a degenerate case. Okay, so so I think Rudin says we do not want fields of one element. Fields are going to have 2 or more elements. Okay, so in particular, 0 shouldn't be 1. Right? You don't want 0 and 1 to be the same thing, because in that case, you're back to your degenerate field again. Right? Because if 1 is equal to 0, then everything times 0 is itself. Right? So any element times 0 would be itself, which means that every element is 0. Okay. So yeah. Okay, and then the last thing, of course, is the distributive property. Right? How the two operations interact with each other, right? You want them to distribute. Okay, and so like we said last time, there are a bunch of other properties that are in fields, but we don't put them into the axioms because they just follow from the axioms. Okay, so let me sort of sketch out some. There are.
Hello.
Hi. Oh yeah, that's right. You're joining the class?
Yeah.
Yeah.
Jackson.
Okay. Yeah. Okay. Okay. Welcome.
Sorry I'm late.
Yeah. Actually, I don't think I knew. Did I know you were joining? Did I write to you an email? No.
No.
Okay. Then I actually don't know who you are. But welcome to the class anyway. Yeah. Sorry. It's my other class. Somebody wrote to me and said I'm joining the class. In any case, okay. So we're talking about fields. So we're just follow along and catch up. Okay. So but just to give you some sense of what's going on, a field is sort of a generalization of the real numbers or the rational numbers, right? The real numbers or the rational numbers, they both have addition, both have multiplication, and those operations satisfy certain properties, right? That the addition and multiplication must both be commutative. Addition and multiplication must be both associative, right? There has to exist. There is an additive identity, something that you add and nothing happens. There's a multiplicative identity, something that you multiply and nothing happens, right? And then there's an interaction. There's a way that these things interact with each other. Right, that multiplication and addition interact distributively, right? So like if you have x times y plus z, that's going to be x times y plus x times z, right? Okay, so a field is just something that a bunch of objects that has a plus, it has a dot, and they satisfy all these properties. Okay, and what we're saying now is that there are a bunch of consequences of those properties, and they just follow from the axioms. Okay. Sometimes I had a student many years ago who said that she had gone to a math camp somewhere, I think University of Chicago maybe, and for the first couple of weeks they just did proofs using field axioms, which sounds like the worst summer high school math camp ever, but because it's very dull. But I guess it's a way to show people how to prove things. It's a way to introduce people to proofs. So, because it's there's just these basic rules, and you see how these basic rules give rise to a bunch of all other properties. Okay, so here's some consequences. We'll do a few propositions that are that give consequences of the field axioms. So first one is that well, whenever x plus y equals x plus z, then y equals z. Okay. So basically showing things that are true, sort of obviously true in the real numbers, actually hold because of the field axioms. Okay. So in whatever field you have, you're going to have this cancellation property. Okay. So the first time you encounter this stuff, you're like, why do we need to prove this? That's so obvious, right? Isn't that obviously true? But what you need to think about is you're not in Kansas anymore, right? You're in the world of an abstract field. You're not in the real numbers anymore, right? All you know is that you have a field and it has two operations and they satisfy these properties, okay? And you need to see, do these things still hold? Okay, do these sort of basic properties still hold? Okay. Second one is that x plus y equals x implies that y equals 0. Third one, that x plus y equals 0 forces y to be the additive inverse of x, right? So this one is sort of saying that there's only one thing that will work like an additive inverse, right? Like, you know that x plus negative x is 0. That's given to you. Oh, I forgot to write those. Sorry. A5, there exist additive inverses. Right, so every element x has an additive inverse, something you can add to it and get to 0, right? And similarly over here, right, there exist multiplicative inverses, right? Every element x has associated with it some sort of, every non-zero element x has a associated multiplicative inverse that you can multiply it by to get to the multiplicative identity. Okay. So what this one is saying is that the additive inverse is unique, right? There's no other, if you act like the additive inverse, you must be the additive inverse. Okay. You can't have two additive inverses. Okay. Two different ones. Okay. the last one says that the additive inverse of the additive inverse is just the original thing. Okay. Which, okay. Okay, so yeah, these are all things that are true in the real numbers, and we want to see, how you. It's more like showing how to put proofs in fields. Okay, so here's the first one, right? You want to show that cancellation is possible. So you say, well, suppose x plus y equals x plus z, right? Then negative x plus y equals negative x plus z. Right? Okay, right? Because you're adding the same thing to the same thing, right? This is the same thing as that, so this plus that is the same thing as this plus that. Okay, right? So okay, and then you use and then negative x plus y equals negative x plus z. So what are we using? We're using the associative property. We're using the associative property, right? Then we get 0 plus y equals 0 plus z, right? We're using additive inverses, right? Then that tells you that y equals z, and we're using the fact that 0 is the additive identity. Okay, so that's how you get from here to here using the field axioms. Okay, so pretty dull, right? I mean, I don't know. It's dull. It's dull. Okay, right. Similarly, for this one, right, you would do something similar. You'd say, well, I'm going to add negative x to both sides, right? You see that if you add negative x to both sides, you're going to get 0 plus y equals 0, so y equals 0, right? For this one, you would add negative x to both sides, negative x, those guys would cancel off, you get 0, y equals negative x, and so on and so forth. Okay, so, right, right, this last d you can prove using c. You would say, well, look, negative x plus x equals 0, right? So negative x plus x equals 0. So that tells me by c, right? C said that if this plus that equals 0, then this must be the additive inverse of this. Right, so by C, you're done. Okay, okay. So, like I said, not the most exciting thing, but yeah. If anybody ever asks you in the future why why this sort of thing is true, you can say by the field axioms. Okay. Yeah. Often people ask, like, well, why is this sort of basic thing true about the numbers? Why is -1 times -1, 1, right? And you can work it out. You can work everything. Those sort of questions you can work out using the field axioms. Okay. Everybody all right? Everybody all right? Okay. So yeah, I'm not sure how much I want to do of this stuff. Let's. Okay. Okay. So there's another proposition. This one dealing with sort of more multiplicative stuff. First one, that 0 times x is the 0 element. The second one, that if x is not equal 0 and y is not equal 0, then xy cannot be equal to 0, right? So this is the no 0 divisors. Right, that you can't the only way you could get a 0 is if one of the things is 0, right? And then third one, that the additive inverse times x equals, I'm sorry, the additive inverse of x times y equals the additive inverse of xy. And then the product of the additive inverses equals the product of the original guys. So maybe I'll do a couple of these, but I'm not going to do all of them. Okay. So the first one the first proof goes like this. You say, well, look, 0x plus 0x equals 0 plus 0x, right? So what are we using here? Distributive, right? So by distributive property, using that. And then 0 plus 0 is 0, right? So you get 0x, right? Because 0 plus 0 is 0, right? By A4, say. Right? And then now we use cancellation, right? So from the previous proposition, we can do cancellation. And so we get that 0x is equal to 0. Okay. B, we'll do proof by contradiction. Suppose that x and y are non-zero, but xy equals 0. Okay. So x and y being non-zero means that so let me write like this. So then xy equals 0, and we're going to multiply both sides by the inverses, 1 over x and 1 over y. Then this is going to be the same thing as that, right? But then what happens, right? You can do some commuting, right? You do some commuting and associating, and you end up with 1 equals 0. Right? Maybe I should. Do people want me to write that out? The commuting and the associating. Okay, good. Right. So yeah, so you're gonna use the commutativity and associativity, and here you use the fact that well, you use part A, right? Because this times this is going to be 0, right? Part A said that 0 times anything is going to be 0. So we do need. So this part is by part A. This part is by part A, and this part is by the axioms. Okay, and so you get 1 equals 0. But if 1 equals 0, then you're in the degenerate field case, right? And we ruled out degenerate fields. So that's not okay. Okay. Maybe that's enough of that. Let's not use more of your time on this sort of thing. Everybody close your eyes for a second. Raise a finger if you've seen proofs before. Okay, good. Open your eyes, please. Thank you. I don't know. Everybody, see, in the Claremont system, everybody teaches linear algebra in different ways. But of course, you should have seen at least some proofs in linear algebra. So, yeah, there's sort of a range. Some people go super theoretical with linear algebra, and some people go sort of more calculational. But I think no matter what, you all should have seen proofs. Okay, so that's all I'm going to say about fields. That's the basic information about fields. Now we're going to talk about ordered fields. Okay. Before we get there, let me give an example of an ordered set that I forgot to include, which is the complex numbers with the so-called lexicographical ordering. Okay. So by lexicographical order, it just means like the dictionary order. Okay, so like a dictionary. Right. So with the complex numbers, you're gonna have points like a plus bi, some other point c plus bi. Okay. And we want to put an ordering on it. One order you can put is called the lexicographical order. And so you say that, let's call this one W and this one Z. We say W is less than Z if if A is less than C, right? Or A equals C and B is less than D. Okay, so all this is just like the dictionary, right? So cat, right, is less than dog, right? Because you look at the initial letter, right? You look at the initial letter, you compare them, right? And if the initial letters are the same, right? If the initial letters are the same, you look at the second letter. Okay, right? So in this world, right, 1 plus I is going to be less than 1 plus 2I, right? 1 plus I is definitely less than 2 plus 3I, say, or negative I, right? So basically what you're saying is that we say that this one is less than this one if it's to the left or they're on the same line and this one is lower, right? So this W is less than Z. Let me introduce another one, zeta. W is less than zeta because they have the same real value, but the complex value, the imaginary value is bigger for zeta. Okay. So that's lexicographical order on the complex numbers. Okay? Okay, that's sometimes useful to know. Okay, so now we're talking about ordered fields. An ordered field is not just a field plus an order. Okay, so like here's a field and it has an order, but that doesn't make this thing into an ordered field. Okay, ordered field has to be that the order and the operations work together in the way that you would want them to work. So what I mean by that is the following. Let F be a field. And this thing, an order on F. If y less than z implies that x plus y is less than x plus z. Right, so if, let me write this out. If for all x, y, and z in your field, you have that the ordering is preserved by addition, right? So when you have this order and you add the same thing to both sides, it still preserves that order, right? And you have that whenever you have two things that are greater than 0, then the multiplication results in something that's still greater than 0. Then we call this with the order an ordered field. Sheldon.
Can you give like an example of when those two things don't apply? Because I don't know, those just seem like they would always work.
So what you're going to see in the homework is that it's actually impossible to make C into an ordered field. There is no order that will work, that will cause this to be preserved. Yeah. And I don't want to spell it out because that's that one example, the one non-example. But yeah. So what you see in the homework is that, yeah, I don't want to. Anyway, you can try it. So C with a lexicographical order is not an ordered field. Okay, so think about it a little bit, and you'll be able to come up with something that show that where this fails. Okay, but in fact, there is no order you can put on C to make it into an ordered field. And
if we were to go about proving that something is an ordered field,
yeah,
would we first prove that it's an ordered set and then
that's
go
right.
these?
That's right. So you need to show that it's a field, that you have an order, and that the field operations and the orders interact in the way that you would want them to interact. Okay. Okay. So not sure if I should do it or not, but just as we had before, there are immediate consequences of these axioms, right? So at this point, for an ordered field, you're going to have the field axioms, and then you have these two like ordered field axioms, okay? And those things all together cause certain other properties to hold. So let me just write up some of them. So again, sort of basic properties of ordered fields. Okay. First off, that if x is bigger than 0, then negative x is going to be less than 0. Second, that if y is less than z and x is greater than 0, then xy is going to be less than xz. Third, which is kind of just a variant of that, if y is less than z and x is less than 0, then you're going to have the opposite inequality. Next, that for any non-zero x, x squared is going to be positive. So x squared has to be positive for every element. And last, that if you have something like this, 0 less than x less than y, then you also have that 0 is less than 1 over y, which is less than 1 over x. Okay, so these are all things that sort of are obviously true in the reals, and they turn out to follow from the ordered field properties, or ordered field axioms. Right. Let me just do a couple of them. So the first one, suppose x is greater than 0, then this one's kind of straightforward. You add negative x to both sides. Right? And the inequality is preserved. Why? Because we demanded that, right? Okay. Right. So by this is true by one, by the first property, okay? Right? And so 0, right, must be greater than negative x. Okay? Which seems obvious, but you see that we needed this condition. Second one, suppose, say y is less than z, right? Okay. In that case, adding negative z to both sides, we get negative y plus y is less than negative z plus y. Right. So again, we're using property 1. The inequality is preserved when we add the same thing to both sides. Right. And so we get that 0 is less than z minus 1, or z plus negative 1. I'm just going to leave it like this. Okay. But then x was positive, right? X was positive, so when we multiply this, we have a positive number and a positive number. By property 2, we can multiply them and still get a positive number, right? Positive element, not a number. Okay, so we get that the product must still be positive, right? And then you use distributivity, and you get that 0 is less than x times negative y plus x times z. Right? And we know from the previous proposition that this is the same thing as this x times negative y is the same thing as the additive inverse of xy. Right? So we get 0 is less than negative xy plus xz. Right? We add that to both sides. Right? We add xy to both sides, and we get xy is less than xz. Right? Which is what we wanted. We wanted to see that when you multiply by a positive element, then you preserve the inequality. Well, do you have a question?
No. I just wonder, like, from x times negative y, and then you use associative, right? Such as
From here to here?
no, from that to from the
From
last
here
one
to here?
Yeah. So did you use the associative that moves the negative one now?
There is no negative one.
Okay. So
Well, actually, no, there is a negative one, but no, this is just using the previous. Do you remember in the previous proposition we had negative xy equals negative xy equals x negative y. Okay, so that was something I didn't do the proof of, but that was from the previous proposition.
oh, okay.
So that was from C in the previous proposition.
Oh, okay.
Okay. Okay. Okay. So in any case, right. If you have a field and an order, and the operations interact in the way that you like, then you call this thing an ordered field. Okay. So all of this is basically to set up the real numbers. Right. This whole first chapter is basically about the real numbers and the complex numbers, to put them on some sort of more stable theoretical ground. So at this point, now we actually can say what the real numbers are. Like after all of this, definition for the last couple of days, we can say what are the real numbers. So here's the theorem. There exists an ordered field. That one contains the rational numbers as a subfield. Okay, so that is there's some field and it contains the rational numbers, and the addition and the multiplication of this thing will agree with those of the rational numbers. Okay, so it's not like this thing sits inside that field with its own, different addition and multiplication, right? It will, the addition and multiplication from this f will agree with that of the rational numbers. That's what contains as a subfield means. Okay, and 2 has the least upper bound property. Okay. So there is such a field, and we call it the real numbers. R. Okay, so there is such a field. Okay, now Rudin leaves the proof of this to the appendix. It's this kind of really long and complicated proof. So he doesn't in the proof he basically makes a construction that creates this field, but we're not going to go through that. We're just going to, if you want, you can read the appendix, but we're just going to use this fact that we're just going to take this as a fact. There is an ordered field that contains the rationals as a subfield and has the least upper bound property, and we call that thing the real numbers. Okay. Yeah. Yeah. So I think the proof in the appendix uses something called Dedekind cuts, proof by Dedekind cuts. But I haven't looked at it in a long time, so I don't know. For those of you, for your amusement, there is something called surreal numbers that I believe were created by the mathematician John Horton Conway. And there's a book by the computer scientist Knuth, Donald Knuth, called something like Surreal Numbers, or, and it has this long subtitle, like Surreal Numbers, or how 2 ex-math majors turned on to mathematics again and found true love, something like that. So there's a play. The characters are Alice and Bob, right, A and B, and they're these 2 people, and they have given up on mathematics. They're on a beach somewhere, and they find this rock. And on the rock is like some sort of like almost biblical, like Genesis type statement about, lo, on the first day, John Horton Conway created, said that the numbers should satisfy this. And like, oh, what is this? And then they start thinking about it. And on the second day, he said something, right? And it's a really interesting construction where just from, I think, 2 axioms, he creates a whole entire system of numbers that includes the real numbers, but actually goes far beyond it to include like infinitesimal numbers and infinities as well. So like it gives a logically consistent way of creating a system that you can deal with, like what does infinity to the infinity mean? What is 1 over infinity? This sort of thing. So yeah, that's I read it a long time ago. But, okay, we have 11, 12 minutes left. So I don't know how much we can get this done. Okay, so R, right? R, the real numbers. So for us right now, all they are an ordered field that contains the rational numbers as a subfield and also has the least upper bound property. We're going to first show some properties that you probably are familiar with. I don't know, maybe no, you're not. So here are some basic properties of the real numbers that we're going to prove. Okay. The first is called the Archimedean property of the reals, that given any So now we're in R, right? So in R, given any number that is positive and any other number y in R, then there exists an n, a natural number n, such that nx is bigger than y. So given any number in R, right? So here's the picture, right? Given any number, here's 0, here's x, and you're given some other number y. Okay. And what this is saying is that there exists some natural number so that n times x is bigger than y. Okay. In some book, it was described as you can empty a bathtub with a spoon, right? So this is the spoon. No matter how big the bathtub is, some multiple of spoons will empty the bathtub. Okay. So spoon and bathtub. Second one is the following: that Q, the rationals are dense in R. Okay. This doesn't mean anything at this point. It's just think of it as some sort of like cryptic phrase, and we will not. When later we'll talk about what density really means. Okay. This is not the definition of density. So yeah. But so what the second property is that given for all x and y in R, where x is less than y, you're guaranteed a p in Q such that p is between x and y. Okay, so given any two real numbers, you can always find a rational number between them. Okay, so like no matter how tight together the real numbers are, you're always guaranteed a rational number between them. Okay. And this is the one that Bong was talking about earlier, the one that gives this kind of, again, kind of cryptic proof, but it'll make sense. Okay, so proof for the first one. Proof for the first one, so we're going to do it by contradiction. Proof by contradiction. So suppose that nx times y is less than or equal to y for all n. Right? So, right. Suppose there's some positive x and some real y. Some positive x and some real y, and no matter how many spoons you take out, the bathtub is still bigger than that. Okay. Okay. So, what do we have? We only have a couple of properties about the reals that we can use. One is the least upper bound property, and the other is that it contains Q as a subfield. We're going to use the least upper bound property. It's sort of, probably you can guess we're going to use the least upper bound property, right? Because this thing is an upper bound, right? Then y is an upper bound for the set of nx. Create this, you make the set of all the nx's, right? And y is going to be an upper bound for it. But then then the set, let's call it A. A has at least upper bound. So let's call that M. M, the supremum of A. Okay, so we've got the supremum, right? Right. Anybody remember what's done at this point? Does anybody know what happens here? I should have asked earlier, like what's the strategy or this sort of thing. Yeah, Charlotte.
Well, then you can say that m minus x is less than m.
So yeah, so m minus x is less than m, right? So it's, this was the least upper bound, right? So this is not an upper bound, right? So m minus x is not an upper bound of a, right? Since it's not an upper bound of a, there must be some nx, right? So there's some n naught such that n naught x is bigger than or equal to m minus x, right? Right, and then you see that. So then, right. So then you see that n naught plus 1 x is bigger than or equal to m. Right. So then you move the x to the other side, and you see that n naught plus 1 x is bigger than or equal to m. But that says that there is, this is still a natural number, and we get a natural number times x that is bigger than or equal to m. Right? I'm sorry. This should be strictly bigger. Sorry. Okay. So we end up with something that's bigger than m, but that's a contradiction, right? Because m was supposed to be the least. M was supposed to be the least upper bound for this set. Right. But we found something bigger than m in the set. Okay. Okay. Any questions about that? That one's the easy one. The slightly more complicated one, which I hope I can finish, is the second one. Usual. Don't tell me I've lost my notes. Okay, so so the second one is that so proof of 2, right? So given x and y, where x is less than y, we want a rational number, right? We want a rational number such that x is less than. Actually, let me use a and b because that's what I have in my notes, and you're going to get my notes. So you want a rational number such that a is less than mn is less than b, right? Okay, so that's the same thing as saying that na is less than n, m is less than nb, right? That's what we want. We want m and n, natural numbers, such that this holds. Right? So you think about it, we have to have NB and NA far enough that we can choose an integer between them. Right? So you think, our strategy, here's our strategy. We want to choose M and N so that this is true. Well, one thing that we definitely need is that NB minus NA has to be bigger than 1. So notice that we want NB minus NA to be bigger than 1, right? So that we're sure that there's an integer for us to choose in there, right? Right. So, but we can do that. We can, right? Because this is n times b minus a bigger than 1. So we can do it by the Archimedean principle, right? We look at b minus a is positive, right? So let me see it this way. Okay, this is the same thing as saying that n times b minus a is greater than 1, where this is a positive number, right? Right, because a is less than b, right? So first thing to do is use the Archimedean principle to choose n such that, choose the natural number such that this is true. Okay, right. So that's our first move. Okay, and then we do something a little bit. It seems a little bit weird, but you'll see why. And then again by by the Archimedean principle, choose m1 and m2 natural numbers such that m1 times 1 is bigger than na, and m2 times 1 is bigger than negative na. Okay, again, we're using the Archimedean principle, right? That you can choose a number of, there's a number of spoons that will be bigger than this bathtub. So, sorry, I think I can finish this in 1 minute, so sorry. I'll hold you over a little bit. Okay, so in that case, what do we have? We have that negative m2 is less than na, and that is less than m1. Right? So putting these things together, we get that. Right? Okay. So now let capital M be all the integers between negative m2 and m1 such that m is bigger than na. Okay. So you want this. Okay. You choose all the integers between these two numbers, m2 and m1, negative m2 and m1, such that m is bigger than na. And you know that there's going to be that this is non-empty, right? Because m1 is bigger than na. Okay. So it's non-empty. Okay. This is a finite set, right? Because you're going between two numbers. So choose the smallest, right? Let m be the smallest, the minimum of that set. Okay. So m is the smallest integer that is bigger than ma, so you know that m minus 1 must be less than or equal to na, right? M minus 1 must be less than or equal to na. But
why is the equal sign?
what?
Why is there the equal sign?
Well, m is bigger than na, so m minus 1 is not bigger than na. In other words, it's less than or equal to na.
Okay, I just thought like that.
Okay, let me just finish. We can talk after. Sorry. Okay, and so what do you get? You get that na is less than m, right? Here, which is right. M in turn is less than na plus 1, right? Na plus 1, right? And na plus 1, remember, is less than nb, right? Because the distance between nb and na is more than 1, right? So that's based, so by what we required here, right? nb minus na is bigger than 1. Okay, so we're done, right? That m is it, right? That m satisfies what we needed was this. We needed m and n satisfying this relation, and we've got it, right? M is bigger than na, m is less than nb, and that's enough, guys.
Sorry.
You're good. Sorry to keep you over. Sorry.